The chain rule is required when you have a composition of functions, a function within a function. Notation for that can be seen down here. So you say f of g of x, or f of g of x, or f composed with g with respect to x. At right, there are examples of functions that do not require the chain rule to derive and examples that do require the chain rule. So let's talk about what kind of differences we see here. So this is x squared plus 1. That does not require the chain rule. But when we've put an entire square root over the quantity x squared plus 1, then yes, it requires the chain rule. So if y right here requires the chain rule and we're writing it as f of g of x, g of x is the function inside, which makes g of x this little polynomial inside. So in this case, g of x, the inside function, is x squared plus 1. But then it's all under the f function, which is a root. So the f function is square root of whatever is underneath it. We'll call it x. Okay, another thing that doesn't require the chain rule that we did before, just sine x, okay? But what if you're not taking sine of x, you're taking sine of 6x or sine of x plus 5, okay? That changes things. That requires the chain rule. The function that is on the inside is 6x. And the outside, what you're taking of 6x, you're taking the sine of 6x, or what is happening to the product 6x, you're taking the sine of that product. Okay, now the function that is on the inside here, okay, 3x plus 2 does not require the chain rule, but when you're taking that whole quantity and putting it to the power of 5, then yes, your outside function is taking some quantity, we'll just call it x, and putting it to the power of 5. But your inside function is this line, the quantity that's being put to the power of 5, 3x plus 2. The chain rule is not required here, right? But here we have tangent of x squared. This is not tangent squared of x. This is tangent of x squared. If it were tangent x times tangent x, then you would get tangent squared x, is how it would be written. Okay, so this is tangent of x squared. This x right here will not require the chain rule, but since you're taking the tangent of not just x, you're taking the tangent of x squared, this right here will require the chain rule. So in that case, your outside function was tangent, so you're taking the tangent of something, and the inside function was what you're taking the tangent of, which happened to be x squared. It's important to recognize when you need the chain rule and when you do not, and what is your outside function and what is your inside function. So suppose we want to derive a composition of functions. We want to use the chain rule. What is it and how does it work? To make it a little easier to understand visually, I'm going to say, okay, g of x, I'm going to call that u, just so I have one letter instead of this notation, g of x. If I'm calling g of x u, then really what I'm trying to find the derivative of is f of g of x, but g of x is u, so f of u. We're also going to refer to f of u as one letter, so f of u is going to be referred to as y. So really what we're trying to find here is the derivative of y with respect to x of y, given these labels. I'm going to actually use the dy dx notation whenever I can. We will start by deriving. So f is a function of u. So f prime of u would be the derivative of y with respect to its input. What is the input of this function? That is u. So instead of dy dx, we write that as dy du because f is a function of u. Now, g prime of x. This would be deriving the function u, right, because g of x is called u, with respect to the variable of its input, which is x. So when they're asking us to find dy dx, we can actually use our notations in a mathematical sense to help us with this. So cool. Dy over dx. If I multiply dy du times du dx, du over du is 1, and I get dy dx. But what does that mean in terms of f and g if we're given a composition of two functions f and g? Well, the derivative of y with respect to u can be rewritten as f prime of u, and du, the derivative of u with respect to x, can be written as g prime of x. So multiplying the derivative of f with respect to u by the derivative of g with respect to x, we get the chain rule, the derivative of the composition of functions. But we have too many moving parts here. So theoretically, we're given two functions, an f of x and a g of x, and we need to write some sort of formula to find the derivative of this composition. If you remember, we labeled g of x as u. So if we wanted everything in the same terms, we could write g prime of x instead as u prime. Or, which makes more sense, we're actually going to change the one with u written in it. So we'll keep this as multiplied by g prime of x, but we'll substitute g of x into u. So f prime of g of x times g prime of x. That would be how we find the derivative of the composition f of g of x. And this works only when you have f being differentiable with respect to u, and then g is differentiable with respect to x. Basically, can you actually evaluate the derivative there? This right here is the chain rule. In order to use the chain rule, you need to know what is my outside function and what is my inside function, and also when you need to use the chain rule and when you don't. To find the derivative of a composition of functions, we take the derivative of the outside times the inside times the derivative of the inside. Let me say that again. The derivative of the outside times the inside times the derivative of the inside. The derivative of the outside times the inside times the derivative of the inside. The derivative of the outside times the inside times the derivative of the inside. That's the chain rule. Let's try it out. I have a preference. I do prefer using u instead of using g of x. The only thing you have to remember is that u is a function of x. Okay, or whatever variable they've given you. So you need to know what is your inside function and what is your outside function. The inside function, I'm going to call u, would be this quantity, x squared plus 1. And the outer function is basically what is f doing to the u function. It is taking u and it is cubing it. Okay, this is just an easier way for me to visualize it because there's not x's in each that could represent different things. So what I need to know is I do need to know what is f prime of u and what is u prime. So right here I'll take u prime is 2x. Now f prime of u is pop down, power down, 3u squared. Awesome. So when we derive this, y prime is equal to f prime of u. F prime of u is 3u squared times u squared. Awesome. That's the derivative. But wait, you have a u and you have an x. So it all needs to be written with the same variable, right? We're deriving y with respect to x because that's what we started with. So y prime is equal to 3 times u is the function x squared plus 1. And this is to the power of 2 times u prime, which is 2x. Simplify by bringing anything that's not squared to the front. So 2x times 3 is 6x times this quantity squared. Now, that may have seemed a little bit complicated with all of the moving parts. I just wanted you to show how you could break it down bit by bit. I know my inside function is x squared plus 1. I know my outside function is that quantity being cubed. The chain rule is the derivative of the outside times the inside times the derivative of the inside. And there's how I would do this in 2 steps. Once you get familiar with the pattern, once you get familiar doing it over and over and over. Number 2, we're going to rewrite this, first of all, as a power. So f of x, you have a cube root. So I can rewrite this as x squared minus 1 squared, but that entire quantity is under the cube root, which means it's to the power of 1/3. We can do some more algebraic simplification before we apply the chain rule. This power to a power, we multiply and we get x squared minus 1 to the 2/3. Now, we will derive using the chain rule. My inside function is this quantity, and my outside function is this exponent or root, f prime of x. The derivative of the outside times the inside, 2/3, a quantity, and then subtract 1 from 2/3. 2/3 minus 3/3 is negative 1/3. I always write the new exponent before I fill in the parentheses so that I don't accidentally just copy down the exponent that's right here. Okay, that's very important not to forget that, and I think that's what most students forget in the chain rule is to subtract that. Since this is not changing, they forget to change this. So just make sure you keep an eye on that. X squared minus 1, and that is being multiplied by the derivative of the inside. And we can even write that as d dx of the inside. Continuing on, you have 2/3 times this. I guess we could put it in the denominator. I'll do that in the next step though. Times the derivative of x squared minus 1 is 2x. Great. So f prime of x is equal to, I'm going to draw a fraction and decide what goes where. So 2 is in the numerator, and this 2x is in the numerator. but this 3 is in the denominator, and this needs to go into the denominator because of the negative exponent. So I have 4x in the numerator over 3 times the cubed root of x squared minus 1. My favorite thing about the chain rule was when I discovered that I could use it to avoid the quotient rule. Apparently, I was just not a huge fan of the quotient rule when I took calculus. I like it now, but yeah, I really do love the chain rule, and I always prefer the chain rule. So, how do we use the chain rule on this quotient? Well, we rewrite it. G of t can be rewritten as -7, and this whole quantity is to the power of +2. But if I brought it up to the numerator, it would now be to the power of -2. And now, doesn't this look like a more fun function to derive than this one? Well, it does to me. So let's derive using the chain rule. Now it's important to know what is our outside function and what is our inside function. So here we have the inside is this quantity being brought to the power of, the outside is the power of -2. This -7 right here is just a constant. So when you pop this -2 down, just like in the power rule, you're going to multiply -7 times -2. Okay? So pop down, power down. So the derivative of the outside, -7 times -2 is 14. -2 minus 1 is -3. Now I'll put 2t minus 3, the derivative of the outside times the inside, times the derivative of the inside. Now, can you do this in your head? The derivative of 2t minus 3? The derivative of 2t minus 3 is actually 2. Okay, so continue to simplify. I'm going to draw a fraction now and just decide where everything goes. 2 and 14 are in the numerator, so 2 times 14 is 28. And 2t minus 3, this whole quantity is being cubed, but it's being cubed in the denominator. When it comes to simplifying, the most important things that I'm looking for now that we've kind of entered into calculus where the whole roots in the denominator is not as important, okay? No complex fractions, so don't give me a fraction that has multiple fractions within it, and then no negative exponents. Always turn those exponents back into positive by putting the quantity on the correct side of the fraction bar.